Hello everyone. Today we will talk about the earthquakes. In this lecture, you will learn about what are earthquakes, how earthquakes are detected and described, and how earthquakes influence our life. Earthquake is energy release from rocks. The energy comes from forces. Let's talk about what do forces do to rocks in reality. When force applied to rocks, rocks will be deformed. When the deformation to the rocks are elastic, the rocks are resilient. Stress is the local force per unit area that keeps the rocks to deform. Strain is the relative amount of deformation expressed as the percentage of distortion. For example, compression of the rock by 1% of its length. When the deformation to rocks are too much, the rocks fail, break into two or more parts. The critical value that beyond which the rock is stressed to break is called strength of the rock. Now let's see why there are earthquakes. An earthquake can happen is because deformation forces applied to the rocks and the stress on the rocks increase and goes over the rock's strength. When the rocks fail, the stress causes the movement and the displacement in the rock, and also cause the elastic rebound from the deformation, which releases energy and causes earthquakes. This process can repetitively happen to a fault where the strength of rock is relatively small along the fault plane. Two fault blocks creep along the fault plane under stress and release energy. Each episode of releasing energy is an earthquake event. Therefore, earthquakes occur where rocks being stressed and suddenly break along the new or existing fault. The earthquakes are energy releasing event. The energy transformed into waves, which are seismic waves. Seismic waves are ground vibration caused by rocks slipping along the opposite side of a fault. To understand earthquakes, the first thing that we need to describe of an earthquake is the location of the earthquake. The focus of an earthquake is where the rupture of the fault actually happens and where the energy is released. However, unlike the Earth's surface, the interior of the Earth does not have a coordinate system. The location of the focus is hard to directly recorded and described. Therefore, we usually use epicenter and the depth of the earthquake to describe the focus of the earthquake. The epicenter is the point that the earthquake surface directly above the focus of the earthquake. Now let's see physically what happens during a fault rupture. When a fault ruptured, immediately energy is released from the focus of the earthquake. The release of energy produces seismic waves which transmit to all directions. 5 seconds after the shock, the faulting blocks start to rebound on both sides of the rock plane. 5 seconds after the shock, the faulting blocks start to rebound on both sides of the fault plane. The rebound also generates energies and transmits seismic waves to all directions. 10 seconds after the shock, the rupture propagates along the fault plane. The stress applied to the rocks are further reduced to the rock on both sides of the fault plane, further rebound. The stress applied to the rocks are further reduced, and the rocks on both sides of the fault planes further rebound. Meanwhile, more energy released and seismic waves continually transmitted to all directions. 20 seconds after the shock, the rupture has progressed all the way along the fault segment, and the displacement ceased. However, the fault may propagate beyond its particular segment, and more aftershock may occur. This happens during a fault rupture, and in the following part of the lecture, we're going to discuss how the recorded seismic wave signals are related to the rupture and how we can use the seismic waves to understand earthquakes. Seismic waves are transported through the earth and make ground movements. To study earthquakes, the direct signal, the movement of the ground surface must be recorded. The surface of the earth is where to record it. The original purpose of the seismograph and the seismograms are to record movements of the ground surface. Like it is shown in the picture, the seismograph is stationed to the ground, and the ball strained by elastic springs can record movement of the ground in both up and down and lateral motions. The shock to the ground with these different ways of releasing energy are different too. Therefore, there are different seismic waves. Primarily, seismic waves can be divided into the body waves and the surface waves. Body waves also including P waves, the primary wave, and S waves, the secondary waves. Surface waves can only transport through the surface of the earth, while body waves can transport through the interior body of the earth. Between P wave and S wave transport speed is lower than that of the P wave, and the transportation speed of the surface waves are even slower than the S waves. Therefore, when a seismograph stationed on the Earth's surface and recorded a signal of waves that is released from the earthquake, the first recorded signal is P wave, for it is the fastest. The second wave signal is S wave, which is the second fastest. And the last signal is the surface wave, that is the slowest and can only transport through the surface of the earth. The lag times between P waves and S waves increase as the distance between the seismic station and the earthquake epicenter increase. This means that the further away the epicenter is, the longer the S wave will be later than the P wave in arrival. The following video shows you how to use the lag time between the P wave and S wave to determine the distance of epicenter from the seismic station.
Determining the epicenter distance using the wedge method. Imagine for a second you're sitting by a seismometer, and all of a sudden it starts to shake, signifying that an earthquake has taken place. You want to know just exactly how far away that earthquake was. Well, we could do this simply by looking at the report printed out by our seismometer. This is called a seismogram. Now, with a little bit of analysis, this simple diagram can show me how far I am from the epicenter. Here's how it works. First thing we want to look at is the first moment when the seismogram jumps. That signifies the arrival of the P wave. The second significant jump signifies the arrival of the S wave. Now, if we want to know how far we are from the earthquake, how far apart those two arrivals are can reveal that. So what we need to do is a little bit of simple math. We need to calculate something known as the lag time, which is simply the difference between the arrival of the P wave and the arrival of the S wave. Now, in this example, the P wave seems to have arrived at about 9:08 and the S wave at about 9:15. and that would give us a difference in arrival time, also known as a lag time, of 7 minutes. Let's keep that number in mind and take a look at our reference tables. Now, we're going to use a method known as the wedge method to figure out just how far away an earthquake is that would have a lag time of 7 minutes. To do that, we need some scrap paper. And what we'll do is we'll take our scrap paper and we'll align it with our vertical axis, or our travel time axis, on our reference table. And we're going to go ahead and mark off the lag time, which in this case is 7 minutes. I like to make a mark at 0 and a mark at 7, and I also like to label it just to make it very clear. Now, the reason this method is called the wedge method is because once we have the lag time marked, we're going to wedge it in between the two travel curves, the P curve and the S curve, until it lines up perfectly, keeping in mind that the scrap paper needs to remain perfectly vertical. Try and use the grid lines to help keep it in line. Once you have it lined up with the two curves, you simply follow that piece of scrap paper down to the bottom, and that will reveal the distance to the epicenter, which in this case appears to be about 5,400 kilometers. So by simply looking at the lag time and using our reference table, we can figure out how far away we are from the earthquake epicenter.
The motion of different types of waves are different too. P wave is a compressional wave. P wave travel as a series of contraction and expansion, pushing and pulling particles. The compressional direction is the transporting direction within the Earth. S waves are shear waves. Shear waves push materials at right angles to the path of transportation. The rocks' motion are perpendicular to the transportation direction of the wave when the rocks are transmitting the energy of S waves. The surface waves can only transport on the surface of the Earth, and the effects of the motions of the surface waves are more violent to the ground surface. The surface waves can shake the ground in a rolling motion or shake sideways with no vertical movement. The following video will show you how the P wave and S wave and the surface waves of the earthquake will affect the buildings on the ground.
Earthquakes produce different types of seismic waves that can be identified on seismograms. But did you know that each seismograph station produces 3 different seismograms for each earthquake? Why is that? Doesn't one tell you how big the earthquake was? Earth's movement is 3-dimensional, and one component only reflects one direction of movement. If a station had only one component, you would only know about movement in one direction. Different instruments on the seismograph measure 3 types of motion: up-down or vertical motion, north-south motion, and east-west motion. Let's take a close-up, exaggerated look at how a house would be affected by each direction of motion. When the house is shaken in the east-west direction, this shows up on the lower component. Nothing is recorded on the north-south or vertical components. When the house shifts north-south, this shows up on the second line. When the house is shaken in an up-down or vertical motion, only the top seismogram records the motion. During an actual earthquake, the house can move in all directions. Why is that? Earthquakes produce different types of waves, like body waves and surface waves, and these waves travel out from an earthquake in all directions. Body waves, like P and S waves, travel a curving path through the Earth. As a result, they arrive at seismic stations from below. P waves are compressive waves that cause temporary microscopic deformation of the Earth in the direction the wave is traveling. Thus, energy is primarily recorded on the vertical component of the seismogram, with less energy recorded horizontally. S waves move more slowly and are more destructive since they advance with a shearing or back and forth motion. Because S waves arrive later than P waves, They're usually seen on a seismogram as a second pulse. S waves cause deformation perpendicular to the direction of wave travel, which is primarily horizontal or back and forth motion, with less energy recorded on the vertical or up and down component. The slower surface waves, such as Love and Rayleigh waves, move in a more complex undulating pattern and thus show up on all three components. In conclusion, it is the combination of signals that gives seismologists information about the magnitude, distance, and type of earthquake that occurred.
Now let's talk about how to use the seismic signals to find the earthquake epicenter. The following videos show how to use the triangulation method to do so.
Okay, so let's take a look at how to locate the epicenter of an earthquake using the triangulation method. All right, so here is a map of the world, and we're going to zoom in on a particular region. We'll look at North America, and let's imagine that there was an earthquake somewhere in North America. Well, the question arises, where was the epicenter of that earthquake? Now, we may be able to get a general idea of where the epicenter was based on looking at the severity of damage, eyewitness reports, etc. But if you want to pinpoint the actual location of the epicenter, you have to do some calculating. And so let's look at how we're going to do that. First off, in order to pinpoint the epicenter, you need a minimum of 3 seismic stations. So let's pop a few of these seismic stations on the map. Let's say we have one here in California, one up here in Canada, and one down south here, labeled 1, 2, and 3. Now, these are locations where we have seismometers actively monitoring the shaking in the Earth's crust. Of course, we have seismic stations all over the world. In order to use this triangulation method, we need at least 3 of these, or data from 3 of them. So, step 1 is going to be to take the data, the seismograms from each of these stations, and determine each of their epicenter distances. That is to say, I want to know how far point 1 is from the earthquake, how far point 2 is from the earthquake, and how far point 3 is from the earthquake. And this is fairly easily accomplished. You would simply find out the difference in arrival times for the P waves and S waves, and then use a travel time graph to calculate the distances. So let's say you have done that, and you have established that seismic station 1 is approximately 700 kilometers from the earthquake. So something like this. But the problem is, we don't know if it's 700 kilometers in this direction, in this direction, in this direction. We don't know. It could be 700 kilometers in any direction. So what we can do is draw a circle around point 1 with a radius of 700 kilometers. And now we know that the epicenter is somewhere on that circle, somewhere on that line. But again, that's not good enough because we want to pinpoint the location. So let's turn our attention to location 2 and say we did our math and we found that location 2 is 3,000 kilometers from the epicenter. Now again, it could be 3,000 kilometers in any direction. So we will draw a circle around point 2 with a radius of 3,000 kilometers. Now notice something. If you did this properly, your circles should intersect, most likely in 2 places. And what that means is that the earthquake had to happen either here at this intersection or here at this intersection. But again, that's not good enough because we want to know exactly where the epicenter was, which leads us to station 3. We take our seismogram, we do our math, and we determine that station 3 is approximately 3,500 kilometers from the epicenter. So, again, it could be in any direction, so we take a drawing compass and we draw our circle with radius 3,500 kilometers. Now, if this works out properly, all 3 circles should intersect in one single point, and that point is your epicenter, shown by the pink star. This is what we call the triangulation method for locating the earthquake epicenter.
After locating the earthquake epicenter, the most thing we care about is how big the earthquake is and how much damage the earthquake caused. Where there are different scales to measure the magnitude of earthquake, including Richter magnitude, moment magnitude, and the shaking intensity. and the shaking intensity. The Richter magnitude is determined by using the largest recorded seismic wave and the distance from the epicenter to the seismic station. The chart used to determine the Richter's magnitude consists of three scales. The scale on the left is the distance from the epicenter to the seismic station. The scale on the right is the recorded largest amplitude of seismic waves from the seismic station for the earthquake. Plot the distance and the amplitude on the scale. Connect the two plots. The intersection in the middle with the scale of Richter magnitude is the result of Richter magnitude of the earthquake. The moment magnitude is a measurement of earthquake more directly related to the physical properties of the faulting that causes earthquake. The moment magnitude of earthquake is defined as average slip across the rock break. It increases by about 1 unit for every tenfold increase in the area of faulting. Although both Richter's method and the moment method produce roughly the same numerical values, the moment magnitude can be measured more accurately from the seismic station, and it can also be determined directly from field measurements of the fault. From the picture, we can see that large earthquakes occur much less often than small ones. A very simple relationship between earthquake frequency and magnitude can express this observation. Worldwide, approximately 1 million earthquakes with magnitude greater than 2 take place each year, and this number decreases by a factor of 10 for each magnitude unit. Therefore, there are about 100,000 earthquakes with magnitude greater than 3, about 1,000 magnitude greater than 5, and about 10 with magnitude greater than 7. According to this statistical rule, there should be on average about 1 earthquake of magnitude of 8 per year. In fact, magnitude 8 earthquakes occurred on average only once every 3 years, which implies that there is an upper limit to how big fault ruptures can be. Shaking intensity, earthquake magnitude, does not by itself describe the earthquake hazard. It is a method for estimating the intensity of earthquake shaking directly from an event's destructive effects. The table shows the scale that remains in most common use today, called the modified Maselli intensity. This intensity scale assigns values to Roman numerical from 1 to 12 to the intensity of the shaking at a particular site. For example, a location where an earthquake is just barely felt by a few people is assigned an intensity of 2, whereas one that was felt by nearly everyone is given an intensity of 5. Numbers at the upper end of the scale describes increasing amount of damage. By making observations at many sites, and interviewing many people who experienced the earthquake, seismologists can make maps showing contours of earthquake intensity. Although the intensity are generally highest near the fault rupture, They also depend on the local geology. For example, for sites at equal distance from the rupture, the shaking tends to be more intense on soft sediments than on hard basement rocks. This map shows the location of earthquakes around the world. We can see that most of the earthquakes happen to the plate boundaries. Rarely there are also earthquakes that happen in the interior of the plates. From the color of the plots, we find that the depths of earthquakes are shallow at the divergent boundaries, while the earthquakes of deep depths happen at the subduction zones. This is because that the divergent boundaries are associated with the extensional forces and the normal faults. The normal faults are all at shallow depth. In contrast, at the subduction zones, the subducted plate is in contact with the lithosphere of the overriding plate, and the subduction motions leads to fault ruptures all the way along the contact between the two plates. This is the reason earthquakes with a deep focus can happen along subduction zones. Most of earthquakes happen at plate boundaries. However, unlike the illustration of the plate boundaries, a plate boundary can rarely be described as just one linear fault, particularly when the plate boundary involves a continental crust. In reality, the zone of deformation between two moving plates usually comprises networks of interacting faults, a fault system. The fault system in Southern California is a good example to show that. The complexity of the fault system is one of the reasons earthquakes are impossible to predict. So, if earthquakes cannot be precisely predicted, what we can do to reduce the impact of earthquakes to our lives. As geologists, like what we do now, we can map the locations of seismic hazards, combine local geology to carefully assessing seismic risks. Even though we cannot predict when the earthquake could happen or how big the earthquake would be, based on the previous seismic hazards and the local lithology and the geologic structures, we can assess the risk levels of the area. Based on the likelihood of earthquake hazards in an area, we can make policies accordingly to reduce the earthquake impact in planning. For example, make land use policies to avoid developing economic or industrial centers in the regions of high risk. In the area with high risk, we can make proper emergency planning to reduce the loss to a minimum with hazards. And the government can also make policies on earthquake engineering so that the infrastructures can be built in preparation against the earthquakes.